Hello everyone, welcome back to TV Math Hub. If you are preparing for reanalysis, calculus, or you just love diving into the foundations of numbers, today's video is for you. We shall be tackling 4 key questions on subsets of real numbers by talking about the maximum, minimum, supremum, and infimum of the subsets of real numbers. We shall talk about the Archimedean property. We shall also look at rationals and irrational numbers, and also we shall look at the classic proof of why root 2 is an irrational number. So basically, make sure you stick with me up to the end of this video, and if you find this video helpful, don't forget to subscribe, like, and share this video to your friends. We shall not waste any more time. We shall look at question number 1. For question number 1, it says, for each subset of R, determine the maximum, minimum, supremum, and infimum of these given sets. So we shall begin with part 1, which is 2 to 5. Okay, so looking at this one here, we need to determine the maximum, minimum, supremum, and the infimum. So let us look at part 1, which is about the set which is 2, then 5. So talking about this set here, let us look at this set. This is what we call the closed interval. So it includes everything from 2 to 5. It includes everything from 2 to 5. So if, for example, if x is n real number in this given set such that 2 is less or equal to x, or less or equal to 5. So x takes up all the values, or x takes up all the real numbers starting from 2 up to 5. So it means 2 and 5 can be the value of x. Meaning that if you are to mention such numbers here, you must begin with 5, you must end with 5, and you must write all these other numbers within this given interval. So such a set is a set which is having x, for which x is lying between from 2 up to 5, and not forgetting that your x is a real number. So such a set is the set that includes a 2 and includes a 5. So basically, we need to talk about the maximum, the minimum, infimum, and the supremum. So to talk about the maximum is the greatest number within such a set. If you are having this set, so what is the greatest number in this set? What is the greatest element of that set? That is what we call the maximum. Then to talk about the minimum, that is the smallest element of this set. The smallest element of the set, meaning that that element must first of all be inside this set. To be the maximum or to be the minimum, the element must be inside that given set. However, to talk about the supremum, to talk about the infimum, for the supremum of this given set. So if this is our set S, so the supremum of this set may or may not be part of this set. May or may not be part of the set. So meaning that the supremum can be part of the set, or it may not be part of the set. However, the supremum deals with what we call the upper bounds. So you must know what is the bound of this set. And if it is the bound, what is the least upper bound? What is the least upper bound? So the least upper bound is what we call the supremum of this given set. So meaning, for it to be the supremum, then it must be an upper bound, and if it is an upper bound, then it must be the least upper bound. To talk about the infimum of the set, infimum of such a set, the infimum should first of all be a lower bound. It should be a lower bound, and if it becomes a lower bound, then it must be the greatest. It must be the greatest lower bound. It must be the greatest lower bound. The infimum, as we said for supremum, it can be part of the set, can be in the set, or it may not be in that set, or may not be in the set. The same applies to the supremum. However, for maximum and minimum, that element must be within that given set. So you have to be careful there. Now let us look at part 1. So to look at part 1, which is about 2 and 5, we have seen that such a set is a set of elements x for which x lies from 2 to 5, where x is our real number. So if you are having such a set, you realize that 2 is part of this set here, 5 is part of this set. So let us talk about first what we call the minimum. So what will be the minimum? So looking at this set, you realize the smallest, you realize that the smallest number inside this set here, the smallest number that will be inside this set will be 2. This will be 2. So minimum will be 2. Minimum is the smallest number or the smallest element in this given set. Then 2, we talk about the maximum. Let us talk about the maximum. So what will be the maximum? So the maximum of this set will be, so what will be the biggest element? So if you mention all the numbers starting with a 2 up to 5, so what will be the greatest number in that set? Since 5 will be part of this set, it means the greatest number will be 5. Then we talk about the infimum. Let us talk about the infimum of this set here. So the infimum of this set is, we look at this set here. So what is the lower bound? So the lower bound is 2. So it means other boundaries can be there as well. So for example 1, for example 0, all those are boundaries of this given set. 1, 0, negative, 1, negative 2, all that. Those are what we call the bounds. But what is the greatest? If you have 0, 1, you have 2, you have others negative 1, what would be the greatest out of these? So the greatest will be 2. So the infimum is the greatest lower bound, and that will be 2. Then we look up at the fourth one, that is what we call the supremum of this set. So the supremum of this set here will be, so the supremum, what is the upper bound? So the upper bound, when you look at this one here, the upper bound of this set starts from 5. We have 5, we have 6. All of these ones are bounds, the upper bounds. All of these are upper bounds. But which one is the least upper bound? The least upper bound out of these bounds will be a 5. So we have our minimum as 2, maximum as 5, infimum as 2, and then the supremum as 5. So basically, that is about part 1, which is 2 and 5. And from there, I hope it is very easy to look at the minimum, maximum, infimum, and supremum. As we said, the most important thing when you are looking at minimum and maximum, those values must be within that, must be inside the set. But the infimum and supremum, it is not a must. It may or may not be part of the set. So let us look at part 2. Let us talk about part 2. So part 2 is about -1 to 5. So -1 to 5, we have -1 to 5. So it is open at this given end. So that is what we are having. So we need to also look at the minimum. We need to talk about minimum. We need to talk about maximum. We need to talk about infimum. We need to talk about the supremum. So basically, this set here is such a set where you have x for which you have -1 is less or equal to, this one is crossed here, to x less than 5, where your x is a real number. So this is your set. So you can write this as an interval in this form. So this format here helps you to know which value is included in that set and which value is not included. So when you look at this set here, it starts with numbers from -1 and up to 5, but 5 is not part of this set, meaning that it stops like 4.999 something. So 5 is not an element of this set here. So when we are looking at minimum, we need the smallest element of this set. What will be the smallest element in this given set? The smallest element will be -1. Then what will be the maximum? Maximum must be the greatest element in this given set. So when you look at this, you look at the elements of this set move up to 5, but 5 is not included in this set. So for this case, we don't have maximum. because whichever number you think about, there will be a number that will be greater than that. For example, if you say 4.999 is the number which is the maximum number, then there will be a number like 4.99991. So whichever number you think about, which is between 4 to 5, there are very many numbers, infinitely many numbers. So since 5 is not part of this set, we cannot have any other number within this set that will be the greatest. So we have no maximum. So we have no maximum for this given set, because whichever number you think about that is close to 5, there will be a number that will be above it. So for that case, we have no maximum. We talk about infimum. To talk about infimum, we look at the bound. So this is bounded below by -1. So if it is bounded below by -1, is -1 are the greatest lower bounds? That will be true, because if you think about any other number which is less than 1, -1 will always be greater than such a number. So the infimum for that case is -1. And as we said, the infimum and the supremum may or may not be part of that given set. So that's why we can have -1 there. So let us talk about the supremum. When you look at the supremum, that is the bound, the upper bound. So first of all, we look at the upper bound. The set here, all these elements here, will be less or equal to 5. All the elements within this given set will be less or equal to 5, which means 5 qualifies to be an upper bound. But also when you think about other upper bounds like 5.1, 5.2, 6, 7, all those other bounds will actually be greater than 5. So 5 will be the least upper bound. And for that case, the supremum of this given set will remain 5, though 5 is not the maximum. Though 5 is not the maximum, but it qualifies to be the supremum, because all the elements of this given set, whichever elements you write for this given set, they will be less or equal to 5. So for that case, 5 is the supremum, because it bounds it from above, and nothing smaller does. No any other element which is smaller than 5 will be an upper bound. Okay, so that is basically about part 2. So we shall look at part 3. We shall look at part 3. It is open on both ends, 0 to 7. So part 3, we have 0 to 7. So let us look at part 3. So part 3, we are having 0 to 7, which is open on both sides, 0 to 7. So looking at this, this set can also be constructed in a way that you can have this set as a set X containing X elements, but X is an element which is between 0 and 7. So don't put this unless it is a closed one. So where our X is from a set of real numbers. So this is our set. And when you look at this set here, you realize this is what we call an open interval. This is an open interval. It is open on both sides. So we have some closed and some open, like the one we have seen, and the closed one as the first one. So when we look at this, we need to come up with the minimum, we need to come up with the maximum, we need to come up with the supremum and infimum. So we need to come up with the supremum and the infimum of this given set. So to look at the maximum and the minimum, as we said, those elements must be part of this set. So when you look at this set here, it does not include 0, it does not include 7. So the only elements which are included are the elements between 0 and 7. So the endpoints or the end values are not included. So no endpoints are included here. So for that case, when we are to look at the minimum, we must look at the value which is within this given set and is the smallest. So since 0 and 7 are not part of this set, 0 cannot be the minimum because it is not part of this set. But which other number will be the smallest? If you think about a number like 0.00005, if you think about this one as the smallest, then what about that other number which is 0.00005? So such a number will also exist. So whichever number you think about, there will be a number which is are smaller than that number, and they will even be close one another. So it is not possible to get a number which is the smallest out of these ones when 0 is not the smallest number. Whichever number that is close to 0 will be as the smallest. So there will be infinitely many numbers. You cannot get the smallest element within this given set. So for this case, we have no minimum. Here we have no minimum. Then we talk about the maximum of this set. The maximum when 7 is not part of this set, so 7 cannot be the greatest element of this set since it is not within this given set. So which one will qualify? Is there any other element that will qualify within this given set? There won't be any other element that will qualify, because whichever number you think that is very close to 7, there will be some number which will be greater than that. So we also have no maximum. So we have no maximum. Then supremum, that is the upper bound. So all these other elements, all the elements within this set cannot exceed 7. So 7 will be the element which will be greater or equal to elements within this given set. So for that case, 7 qualifies to be an upper bound. And when you think about any other number, there won't be any other smaller number which is smaller than 7 that will qualify to be the upper bound. And for that case, 7 qualifies to be the supremum. 7 will qualify to be the supremum. Then you talk about infimum. Infimum, that is the lower bound first. 0 is the lower bound because no any other element within this set here is exceeding 0 on the lowest side. So when you look at that, 0 will be the lower bound. But again, will there be any other number that is greater than 0 which will qualify to be the lower bound? That will not be possible because 0 is the greatest lower bound. For any other number that you choose that will be greater than 0, then that number there will not qualify to be the lower bound. So for that case, 0 becomes the infimum of this given set. So next we look at 2 and 6. 2 and 6. Next we are having 4, which is 2 and 6. So this one, I hope it should be easier for you now for the different numbers that we have seen. This one is describing a set. This one is describing a set which is of elements between 2 is not part of this set, but 6 is part of this set. And x is an element from the set of real numbers. So this will be our set. And for that case, if this is our set, first of all, 2 is not part of the set, but 6 is part of the set. So any element that is above 2 but is less or equal to 6 will be within this set. So let us talk about the minimum of this set. We talk about the maximum of this set. Let us talk about the supremum of this set. And next, let us talk about the infimum of this set. This will be your trial question. So please make sure you try out this. Get the minimum, get the maximum, get the supremum, get the infimum, and put it in the comment section. Put the minimum, the maximum, the supremum, and the infimum. I will check within the comment section for those that will have passed that number. This should be easier for you because we have at least seen the related questions. So make sure you try out that and put that one in the comment section. Okay, so let us look at the next one, 5. So 5, let us look at 5. So 5 is saying we are having this set here, 1 over n, where n is an element from the set of natural numbers. So first of all, it is important that you first list the elements of this set so you can know which one will be will qualify to be the minimum, will qualify to be the maximum, and so on. Okay, so let us first of all look at this set. So if this set here is our set S, if this is our set S, what will be this set equaling to? Let us start with n equaling to 1. N is from the set of natural numbers, so we start with n equaling to 1. If n is equal to 1, what will be this one? The first element will be 1 divided by 1, which is 1. The next element will be 1 divided by, so we are taking n equaling to 1, 2, 3, 4, and so on. So this is 1 over 2. The next one is 1 over 3. The next one is 1 over 4, and this goes on. So it is important you try some other bigger values. Maybe it goes on to 1,000, it goes on maybe to 1 million, something like that. So put it there. So try and see where this one is ending to. So where does this one end to is what is important. Okay, so having looked at the elements of this set, you realize the elements are decreasing. So the first element, if we try to write them, is 1, 0 0.5, 0 0.33, and so on. 0.25, it keeps on reducing. This is 0.001. Next one is 0.000001, and it continues in that way. So you realize all these numbers here are approaching a single value. They are approaching a single value. So this is approaching at some value. Which value is it? Because when you see this one, it keeps on reducing. It keeps on reducing. So it keeps on reducing, and it means all these ones are approaching to a single value, which is a 0, because it is reduced 0.00000. So this these values are approximately equal to 0. So when you look at this set here, you realize this set is consisting of numbers 1 less or equal to. So if S is an element from this set here, if S is an element from this set, so less S less than 0. So these numbers are contained within this range. These numbers are contained in this range, which is from 1. 1 is part of this set, but they are moving, approaching 0, which means they might not reach 0. There will be, this number here is not 0. So they are approaching 0, but they will not reach a 0 because there is no possibility of getting a 0. So for that case, it means this is our set S. So this is our set S. So if this is our set, which is having 1 less or equal to S less or equal to 0, so for this case, you must now be in position to get the minimum of this set. You must be in position to get the maximum of this set. You must be in position to get the supremum of this set and the infimum of this set. And the infimum of this set. So if you are having such a set here, 1 less or equal to S less than 0. So what will be the minimum? So the minimum is the smallest value in this set. Okay, I can still rewrite it very well so it cannot confuse you. So this is 0 less than S. S is an element from this given set, less than or equal to 1. So what will be the smallest value? What will be the smallest value? Okay, so it should be written like this. So it should be written as S is in this range here. Okay, we have it here. So it should be the elements of S. If S is picked from S, it means it should be from 0 less than S less than OS equal to 1. So 1 is part of this set here. 1 is part of this set. So this set here, we are saying, can also be written as 0 is less or equal, 0 is less, S less or equal to 1. Because 0 is not part of the set, but 1 is part of the set. So when you look at such an interval, as we have seen in our previous cases, then you must be able to see that no minimum exists. There is no minimum. There is no minimum because you realize 0 is not part of this set. Then for the maximum, we should be able to tell that one easily. So the maximum is 1. So maximum is 1. Maximum is 1. So the maximum of this set is 1 because 1 is part of this set. 1 is part of the set, which is here. Okay, and then supremum, no number exceeds 1 from above. So 1 is the upper bound and 1 qualifies to be the least upper bound. So 1 qualifies still. Infimum of this set, the infimum of this set, the infimum will be 0 because all of them, there is no number or no element here which will be the lower bound. So the 0 will be the lower bound, and for that case, when you are to consider other bounds, 0 will be the greatest lower bound. So 0 will qualify to be infimum. So we shall not have the minimum, but we shall have the maximum, we shall have the supremum, and we shall have the infimum. So that is for that, for our case number 5. Okay, so that one is done. Let us look at the next one now. Let us look at the next one. So here, before we come to the next one, we said all these terms, all these elements are approaching 0, but you will realize that no any other element within this given set will ever go beyond what? Will ever go beyond 0. So that's why we are taking, or we are including 0 in part as part of our set. But as we said, 0 is not part of this set, but the elements, or the elements of this given set are simply approaching this. They can never go beyond this value, which is a 0. Okay, so I hope that one is very clear, and if that is the case, we shall look at the next one, which is part 6. Okay, so let us look at part 6. So in part 6, we are having -1 to power n, -1 to power n. So our part 6, we are having our set, which is consisting of -1 to power n, -1 to power n, where this n is an element of the set of natural numbers. As we said, it is very important to first list the elements of this given set. So we are taking our n as 1, 2, 3, 4, and so on. So our set, if this is our set S, so what will be in that given set? So this will be -1 to power 1, that will be -1. -1 to power 2, that will be +1. -1 to power 3, we are putting these values where there is n, that is -1, +1, -1, +1, and so on. Okay, so that is basically what we are having. So this is an alternating sequence. This is an alternating sequence which alternates between -1 and 1. So this alternates between -1 and 1, and so on. So this set here, is simply consisting of two elements, -1 and 1. It is alternating between -1 and 1. So it consists of elements -1 and 1. So if it consists of elements -1 and 1, what will be the minimum of this set? What will be the maximum? What will be the supremum? What will be the infimum? So minimum is the smallest value, and it must be within this set. When we look at this, you realize our smallest value is -1. Maximum must be the greatest value within this set. Greatest value will be 1. And for that case, if you already have the minimum, you already have the maximum, the minimum will always be, if the minimum exists, it will be the infimum automatically. And if the maximum exists, it will be the supremum automatically. However, the vice versa does not occur. If you have the supremum, having the supremum, it does not mean it will be the maximum. And having the infimum, it does not mean it will be the minimum. So, but if the minimum exists, it will be equal to the infimum. And if the maximum exists, it will also be equal to, if the minimum exists, it will be equal to the infimum. And if the maximum exists, it will be same as the supremum. However, the vice versa does not, is not true. The vice versa, if you have the supremum, it does not mean you will have the maximum. And if you have the infimum, it does not mean you will have the minimum. Okay, so basically let us look at the final one, that is part 7. So the final one is n, and n is an element of that. Okay, so let us look at 7. So you are having the set n, where n is an element of the set of natural numbers. So if S is this set here, so what will be the elements of this set? Start with n equaling to 1, put 1 here, it remains 1. Put 2 there, it remains 2. Put 3, it remains 3. So that is that given set. So this set here, you must know where this set is tending to. For example, if n is 100, it means this set here will also be up to somewhere like 100. Then it continues maybe 1000. It continues, and so on. So as n keeps on becoming bigger, the elements of this set will also be becoming bigger. So there is no end point for that case. So when you look at this, this is simply the set of natural numbers, and they continue up to infinity. They continue up to infinity. So we need to look at what will be the minimum of this given set. So what will be the smallest value in this set? The smallest value, as we can see, it is consisting of 1. So 1 will be the smallest value. Okay. So next, when you look at again maximum, do we have a maximum value within this set here? When you look at what we have, so you realize we don't have the maximum. So here we don't have the maximum because this one continues up to infinity. So whichever value you think of to be the greatest, there will be some value which will be greater than that. Okay, so let us look at the supremum of this set. Supremum of this set, the set is going up to infinity. So does it have a supremum? So when you think about this, can we get a number which would be the bound, the upper bound? Can we get an upper bound here? And which upper bound will be now the least among the upper bounds? That one is technically not there. So the supremum is infinity. So basically, no supremum for this case. So whichever number you think of, there will be any other number that will be above it. So basically, we shall have no supremum. Okay, so let us talk about the infimum. Do we have the infimum? Of course, since the minimum already exists, then the infimum will also exist, and that will be 1. So that is all about our first question. That is all about the first question. And please don't forget to put your answers for this question number 4 about the set here, which is 2 and 6. So get the minimum, maximum, supremum, and the infimum. So I hope you have really understood on how we can get the maximum, minimum, supremum, and the infimum of any given set. So that is for question number 1, and we shall now look at question number 2. So for question 2, we need to state and prove the Archimedean property. So let us look at the statement for Archimedean property. So the Archimedean property states that if x is a positive real number and y is any real number, then there exists a positive integer n such that when you get n times x, you will get a value which is greater than y. In other words, we are saying that for all the values of x and y that are from the set of real numbers, for all x and y that we pick from R, provided that x is a positive value, that is x is greater than 0, then there will exist a natural number, there exists a natural number n such that when you get n, you multiply it with x, this value will be greater than y. Let us first of all try to understand this statement, if it is true. If you pick, for example, any value, let us call x is a positive value, let us have x as 5. Y is any number, meaning y can be positive, y can be positive, y can be equal to 0, or y can be a negative. So you can choose any number, 5 or negative 5. So if you have x is 5, y is 5, for example, y is 5. Can we get a value n? Can we get a natural number n, which we multiply in this 5 here to get a number which is greater than this? Is it possible? If x is positive, if you get a number, for example, 2, if you multiply 2 with a 5, you will automatically get a number which is greater than 5. So if you have x as a positive number and you have y can be positive, y can be negative. If, for example, y is negative and x is any other number, maybe 1, which is positive. So can I get a number which I multiply in 1 such that this number here will be greater than negative 5? Is it possible such that this statement is true? If you choose a number like, for example, 2, if you multiply 2 with 5, 2 with 1, this value here will be greater than negative 5. So it is true that if you have x greater than 0 and you choose any natural number, there will exist some positive natural number n such that this statement will hold. And that is basically what we need to prove. Okay, so let us look at the proof of this, that if you have x as a positive value, you have y as any number, that you can easily get a positive integer, that you can easily get a positive, you can easily get a natural number or a positive integer n, such that this one would be true. Okay, so let us look at the proof. Already we know that y is any real number. Y is any real number. There is no restriction on y. Y is any real number. So if y is any real number, it means, as we said, y can be positive, y can be equal to 0, or y can be a negative value. In other words, y can be less than 0. Okay? So because there is no restriction on y, so y can be positive, y can be negative, or y can be equal to 0. All right. Part 1, in our proof for part 1, let us first consider when y is less or equal to 0. If y is less or equal to 0, meaning that y is a negative or y is equal to 0. Now we know that our x is greater than 0. We know that our x is greater than 0. That is, x is greater than 0. And also n is a positive integer, meaning n is a natural number, and also n is greater than 0. So since x is greater than 0 and n is greater than 0, what does this one imply? This one implies that when I get n, I multiply it with x, I will get a number which is greater than 0. I hope that one is very true. Because if you have your x as 2, you have your n as any other positive value, maybe 3, x is greater than 0, n is greater than 0. It means when you get 2 times 3, this value will automatically be greater than 0. So that's why we are saying this. Okay, so if this is true, if x is greater than 0 and n is greater than 0, this implies that nx is also greater than 0, which is very true. And for that case, if nx is greater than 0 and you are saying y is less or equal to 0, in other words, this is same as having 0 is greater or equal to y. 0 is greater or equal to y. Now, since I have said x is greater than 0, n is greater than 0, this implies n times x will be greater than 0. And for that case, can we still go on and say this still implies that nx is greater than 0, but this 0 is greater than or equal to y, because I want to get the relationship between nx and y. This is also greater than y, because nx is greater than 0 and 0 is greater than or equal to y. So you have this. So if nx is greater than 0 and 0 is greater or equal to y, what should happen to this? Can we say that nx is therefore greater than y? This therefore implies that nx is automatically greater than y, because we are saying nx is greater than 0 and 0 is greater or equal to y, meaning that if nx is greater than 0 and 0 is greater or equal to y, the only possibility which would be there is that nx is greater than y. And if this is true, then it means this statement is proved. Okay, so which proves the statement that nx is greater than y if x is greater than 0 and n is any natural number. Natural numbers are automatically greater than 0, so that's why we are having this statement. So this one here is true. So therefore, this theorem is true, or our statement is true. Okay, this is part 1. Okay, part 2. Part 1 is done. We have shown this. Part 2, let us look at if y is greater than 0. If y is greater than 0. Here we looked at the case where y is less or equal to 0. Now we are having another case where y is greater than 0. If y is greater than 0, I want us to assume that our statement is false. So let us assume that our statement, if y is equal to 0, let us assume that our statement, that the statement is false. Let us assume that the statement is false. I want us to prove this by contradiction. So let us assume what happens. So if the statement is false, because we are saying if y is greater than 0, let us assume that this statement is false. And our statement is that if x is greater than 0, there will exist n which is from set of natural numbers such that this one is true. Now, if we assume that the statement is false, then it implies, if we assume that statement is false, it implies that nx is actually less or equal to y. Nx is less or equal to y for every n that you pick from the set of natural numbers. For every n that you pick from the set of natural numbers. So if this is happening, if this one is happening, because we shall prove this by contradiction. We want to prove this by contradiction. So we are saying that if y is greater than 0, let us assume that the statement is false. And if this statement is false, it means for every n that you pick from the set of natural numbers, this statement will not be true. So the statement will be nx less or equal to y for every n that you pick. Okay, so let us go on. Let us go on. When you have n of x is less or equal to y, if you have this, then this implies that the set which is A that is consisting of nx, for which n is picked from the set of natural numbers, this set here is bounded above. Is bounded above. That is what we are saying. So we are saying that for nx less than or equal to y, it means the set, remember, these are different values. So if you have n equaling to 1, n is equal to 1, to 2, to 3, to 4, and so forth. So it means you will have n equaling to 1, this will be 1 times x, which is x. So you will have 2x, you will have 3x, you will have 4x. So this will be a set. This will be a set consisting of these elements. But this set is less or equal to y, is less or equal to y. And if the set is less or equal to y, it means all these values here cannot exceed y, cannot exceed y. And that's why we are saying here that the set, this one here, if we form that set, if we let this set here consisting of x, 2x, 3x, 4x here to be A, this set here will be bounded above because they don't exceed. We have seen that these values here, or the elements of this set, don't exceed y. So they are bounded above by y. Okay, so if that is the case, then we shall say that by completeness property, if the set is bounded above, then that set has got what we call the least upper bound. So we shall be saying that by completeness property, by order of completeness property, by the order of completeness property, by the order of completeness property, we shall be saying that if this property says that if the set is bounded above, then this set here has got the least upper bound. So it means A has the supremum. A has the supremum, or the least upper bound. A has the least upper bound because this is bounded above. So if it is having the least upper bound, let's say that that least upper bound is maybe u. So if u is our least upper bound, then this will imply that basically that our set A is less or equal to u. So for that case, this will imply that nx is less or equal to u, and this happens for every n which is picked from the set of natural numbers, because we are saying u is our least upper bound. So it means all the elements from this given set will be less or equal to u. Now, from here, we are saying n is what we call a natural number. If n is a natural number, what does this one imply? It implies that also n plus 1 also n plus 1 into x must hold for this same statement. Because you are saying, let us first list these elements here. You are having 1 times x, which is x. You are having 2x. You are having 3x. You are having 4x. And we are saying all these elements here are less or equal to you. So it means if this one is your n equaling to 3. Then if n equaling to 3 holds, then the same n equaling to 4 must also hold. It must also hold. Meaning that if I add there a 1 on this one here, then it means the next natural number must also be holding. The first natural number was 1. The next natural number is holding. The next natural number is holding. So using the idea from proof by induction, if it holds for n, then it must also hold for n plus 1. If it holds for k, it must hold for the next natural number, which is k plus 1. So meaning since it holds for any x, then it must also hold for the next number after n. The same way we have 2 here, then the next number is 3, the next one is 4. So meaning that if I reach at a point where I am having n, then the next number, which is n plus 1, must also hold. And for that case, that's why we are having that n plus 1 into x must also be less than or equal to u. Since this one here, we are saying this because since n is a natural number, since n is from the set of natural numbers, then n plus 1 is also from the same set. Since n is from the set of natural numbers, it implies that n plus 1 is also from the same set. Because if you have 2 picked from the same from the set of natural numbers, then 3 must also be from that same set. 4 must also be from the set of natural numbers. So if it holds for n, it must also hold for n plus 1. Okay, so from there, let us go on and again say this implies that nx plus x is less than or equal to u. So nx is less than or equal to u minus x. Is less or equal to u minus x. But when you look at this, but u minus x is less than u. But u minus x is less than u. So what does this one imply? What does this one imply, this statement? We are saying this implies that nx is less than or equal to u minus x. But which u minus x is less than? Is less than u. Because if your u is a given value, then when you subtract another value x, remember x is from set of real numbers and x is positive. So if you subtract x, then what should happen? It means this number will be less than u. And if this number is less than u, what does that one imply? What does that one imply? This implies that thus u minus x, which is strictly less than u, strictly less than u, is also an upper bound. Is also an upper bound. Is also an upper bound of a. You are saying that nx is again bounded above by u minus x. Remember, nx before it was bounded above by u. And again, you are saying nx now is bounded above by u minus x. So if nx is bounded above by u, and also u minus x is an upper bound, is it possible? Remember that u is the least upper bound. U is the least upper bound. If u is the least upper bound, then you can, and you have u minus x is also another bound, that one is not possible. That one is not possible, meaning that u is the smallest among the upper bounds, but you are also getting another value which is smaller than u to be an upper bound. So if u is the least upper bound, then it means u is the smallest among the upper bounds. And for that case, it means that u minus x cannot be an upper bound. So we are saying that that's u minus x, which is strictly less than u, is also an upper bound of a. And if this one happens, it means that we have an upper bound. It means that we have an upper bound of a. It means we have an upper bound of a which is less than which is less than the least upper bound. The least upper bound. So you are saying that u minus x, which is strictly less than u, is an upper bound of a. So it means we have an upper bound of a which is strictly less than the least upper bound. So when that one happens, it means this is not true, because you cannot have an upper bound which is less than the least upper bound. That is not possible. That is not possible. So which is false? We have, that is, we have an upper bound of a which is less than the least upper bound, which is impossible. Which is impossible. Or which is false. You can say which is impossible or which is not true, because you cannot have an upper bound which is less than the least upper bound. That one cannot happen. That one cannot happen. So if this is not true, then what does it imply to what we have done? This implies that our assumption, remember we had assumed that any x is less than or equal to y, but we are getting a false conclusion. We are getting to a false conclusion. And if we get to a false conclusion, it means even our assumption was not true. So it means our assumption was not true. So for that case, we shall therefore say, therefore our assumption that any x is less than or equal to y for all the values of n picked from the set of natural numbers is wrong. This assumption here is wrong or is not true. So what is true? Hence, it means there exists an element. It means there exists an element n picked from the set of natural numbers such that nx is greater than y. Such that nx is greater than y. And you have your statement proved. So from here, we shall have proved what we call the Archimedean property. Thus, the Archimedean property will be approved. So that is how we prove the Archimedean property. And I hope it is now very clear to all of us. So you have to follow some of these procedures to prove what we call the Archimedean property. So we have proved this in two different cases by taking y for different cases, y less or equal to 0 and y greater than 0. And we have seen for the two different cases, then this statement is still holding. This statement is still holding. And that's why we say the Archimedean property has been proved. Okay, so let us look at the next part, and that is find the smallest positive integer n such that nx is greater than y in, we are given these different cases. And this is part of the Archimedean property. So let us look at how best we can get n such that this statement holds for the Archimedean property. So looking at part 2. So we are given x as 0.6. We have y as 4. So for that case, let us get the value of n. Let us get the value of n such that nx is greater than y. Okay. So we need n such that n is an element from the set of natural numbers such that nx is greater than y. So n times x is 0.6 should be greater than 4. So if I need this, so this is 0.6, n greater than 4 divided by 0.6 So n is greater than 4 divided by that will give us 6.6666, which is recurring. So we need to obtain the smallest positive integer n. We need to obtain the smallest positive integer n, or we need to obtain the natural number n, which is the smallest, such that this statement holds. So that one here is, so the next positive integer after 6.66 will be 7. So it means the smallest positive integer, don't take the one which is below 6 like 5, it will not hold. So it means our value here, should be n equaling to 7. So n equaling to 7 is the smallest positive integer, such that that statement nx will be greater than y. Because if you are to think about that, if you are to look at if that is possible, if you get 7 times 0.6, does it give you a value which is greater than 4? 7 times 0.6 will give you a number like 4.2, and 4.2 is greater than 4. So the smallest positive integer which will make that statement true will be n equaling to 7. And that will be the answer for 2. Okay, so to part A, let us look at to part B. This is part A. And next we look at part B. You can have it here. So part B, for part B, our x is, let us look at x. Our x is 1.8, then 9. 1.8, x is 1.8, and y is 9. So we need n, which is a positive integer, such that your nx is greater than y. So for that case, you have n times 1.8 should be greater than 9. So 1.8 n is greater than 9, divided by 1.8 by 1.8. So n is greater than, get 9 divided by 1.8, and that will be 5. So n should be greater than 5. So the smallest positive integer we need here will be 6. So n greater than 9. So n should be greater than this. N should be greater than 5. So it means the value of n, therefore the smallest value of n will be, the smallest value of n is 6. The smallest value will be 6. So n equaling to 6 will be true. So if you take n equaling to 5, if you get 5 times 1.8, will this value be greater than 9? 5 times 1.8, 5 times 1.8 will give you 9. So 9 cannot be greater than 9. This is not true. So you must get the number which is next and is above 5. So for that case, you must have n greater than 5. And that number which is greater than 5, the smallest number greater than 5, which is a natural number, will be 6. Because if you have 1, 2, 3, 4, 5, 6, so the number which will be the smallest number after 5 will be 6. The smallest number after this value will be 7. So that is how we get that. So basically that is 2 part A. Okay, that is 2 part A. Then part B is done. Then we have 2 part C. So 2 part C, that is yours to try out. We need the smallest positive. We need the smallest positive integer n such that this one holds. Please try this one out. Try this question here out, this one out, and get the value of n. Put that value in the comment section. So far you have 2 numbers to attempt. You have this one here, 2 part B, 2 part C, and you have from question number 1. Make sure you try those numbers out. Put your results in the comment section. I will check through and see if you have surely been following. So that's where we shall stop for this session, and now we shall look at our next other questions, that is 3 and 4. That will be also in our next video. So make sure you subscribe, like, and follow this video so you can easily get updated whenever a new video is uploaded. So we look at question 3 and 4. We still have very many other questions to look at. Question number 5 is also there. Question number 6, they are there. So make sure you subscribe. Subscribing is completely free of charge. It does not incur you any costs. So let us meet in our next video. We talk about rational numbers. We also prove that root 2 is a irrational number. So let us stop here for this session. So we meet in our next session to discuss questions 3 and 4.
Yeah.